Welcome. In this class we shall discuss the almost unbiased ratio estimator using interpenetrating subsample technique. In the Q-knowledge method we have a sample which is divided into disjoint subsamples. That means the subsamples are disjoint, that is no units are common to different subgroups or subsamples. But here we shall consider overlapping subsamples, that is why interpenetrating subsamples. Now here this is a technique for estimating the bias of a ratio estimator unbiasedly to the second order of approximation based on interpenetrating subsamples. This estimator of the bias may be used to correct the ratio estimator for its bias, thereby getting a ratio estimator which is unbiased to the second order of approximation. So in this method of interpenetrating subsamples, a sample is drawn in the form of M independent interpenetrating subsamples of same size and according to some sampling design we consider here the SRSWR. Maybe for we can use other designs also. Let yi cap and xi cap I equal to 1 to m be unbiased estimates of population totals y and x based on m subsamples. Respectively. So we have y cap equal to y hat equal to 1 by m summation I equal to 1 to m yi cap and x cap equal to 1 by m I equal to 1 to m xi cap. So there are two ratio estimates can be formed to estimate R, that is equal to y by x. So these are one R1 estimate, that is equal to y estimate by x estimate, estimate of total of y divided by estimate of total of x. Second ratio estimator we can form Rm cap, that is equal to summation I equal to 1 to m yi cap by xi cap, that is equal to summation I equal to 1 to m Ri, where Ri equal to yi cap by xi cap. That is the mean of the two ratios. So here we have seen that R1 cap is biased on a single ratio. This is a single ratio, and again Rm bar, this is also biased, but mean, this is the mean of m ratios. This is the mean of m ratios. So according to the sample size in each of the subsamples, when subsamples are large, we have bias of R1 cap equal to bias R1 cap, that is equal to 1 by x bar square or variance of x estimate minus covariance of y estimate x estimate. So this is equal to 1 by x bar square r divided by m square summation I equal to 1 to m variance of xi cap, and this is minus 1 by m square summation I equal to 1 to m. This is covariance of yi cap and xi cap. Now variance of y cap, that is equal to 1 by m square summation I equal to 1 to m variance of yi cap. Similarly also variance of x cap, and this is also equal to sum of the variances because the samples are independent. So now bias in R1 cap equal to one by x bar square into 1 by m square summation I equal to 1 to m r variance of xi cap minus covariance of yi cap xi cap. Now this is equal to 1 by m square summation I equal to 1 to m bias in Ri. Now where bias in Ri equal to 1 by x bar square r variance of xi cap minus covariance of yi cap xi cap. Now bias in Rm, second ratio estimator, Rm cap equal to 1 by m summation I equal to 1 to m bias in Ri. Now we have seen that bias in Rm cap is here is m times bias of R1. But so we have bias Rm cap equal to m times bias R1 cap, that is Bm equal to m into B1. So now this shows that the bias of the ratio estimator Rm cap, that is Bm, is m times bias of the usual ratio estimator R1 cap. Now there are variances. We shall now find the variances correct up to first order of approximation. So V1, that is equal to variance of R1 cap, that is equal to 1 by x bar square variance of y cap plus r square variance of x cap minus 2r covariance of y cap x cap. Now this is equal to 1 by x bar square 1 by m square summation I equal to 1 to m variance of yi cap plus r square variance of xi cap minus 2r covariance of yi cap xi cap. Now this is equal to 1 by m square summation I equal to 1 to m variance of ri, that is equal to variance of rm cap, that is equal to vm. Now we have seen that the two estimators r1 cap and rm cap are such that their variances are equal, but the bias of rm cap is m times the bias of the r1 cap. Therefore this r1 cap is preferred than rm cap. Now we can find expectation of rm cap minus r1 cap, that is equal to bm minus b1, that is equal to m b1 minus b1. So this will be m minus 1 b1. So that implies expectation of rm cap minus r1 cap by m minus 1, that is equal to b1. Hence an unbiased estimator of b1 is given by b1 cap, that is equal to 1 by m minus 1 rm cap minus r1 cap. So here we find the unbiased estimate of the bias of the ratio estimator r1. So now once the approximate bias is estimated unbiasedly, the ratio estimator r1 cap can be corrected for its bias. So expectation of r1 cap equal to r plus b1. So that implies expectation of r1 cap minus b1 equal to r, that is equal to expectation of r1 cap minus expectation of rm cap minus r1 by m minus 1, that is equal to r. So that implies expectation of r1 cap minus rm cap minus r1 by m minus 1 equal to r. This implies expectation of m r1 cap minus rm cap by m minus 1, that is equal to r. So to the second order, so the corrected estimator RC cap may be termed as the almost unbiased ratio estimator, since it is only unbiased up to the second order of approximation, and the variances of R1 cap and RC are same. So RC cap we denote, this is M R1 cap minus Rm cap by M minus 1. So this is an almost unbiased ratio estimator for the population ratio R. Thank you.